In this system, the inertia was all about the mass itself. In this case, there were two masses. And the amount of energy was developed by just one of them. So we recognize that the system had a finite amount of energy, so that when we allowed that ball to drop, the amount of energy in the system was directly attributed to the two forms of kinetic energy that were there. When we changed the mass of the cart, it didn't change the energy of the system. It reduced the velocity of the cart and the velocity of the ball. That was simple. That was straightforward. It's not going to be as obvious what's happening here, but I want to use a kinetic energy example because I think it will demonstrate this the best. So to use a kinetic energy example, I want to take something that's just simple. So just a bar. And we're going to rotate the bar. Let's rotate it about its center. So I'm going to put a point in the middle to indicate we're going to rotate the bar about its center. And as I've indicated, this rotation is going to be out of the board towards you. Right-hand rule suggests that we're looking at a rotation in this direction to support the right-hand rule. We talked about the right-hand rule yesterday, correct? So, wrap my fingers around the axis in the direction that my thumb should be pointing in the direction of that dot, so that's out of the board. My fingers tell me it rotates like that, so it's going to be spinning that way. Are we good? All right, so let's assume that this object is something that I could pick, like pieces of it. Like maybe it's just a bunch of Lego pieces all together, and we're spinning it, and I'm going to take one of the blocks that makes up part of it, say here. One of the block pieces, say over here, and one of the block pieces, say over here. So I'm just going to focus on these three blocks for just a minute for this demonstration. If this is spinning with a spin rate of omega, then I recognize by looking at it that block 1 is probably traveling the slowest of the three pieces. Although it's part of the system and has angular speed omega, its velocity is related to how far away from the axis of rotation it is. And from yesterday, we realized that that's a proportionality. The further away I am from the axis of rotation, the faster I am going. So block 1 is the slowest, block 2 is the fastest, and block 3 is probably somewhere in the middle. Fair enough? So if I want to know the kinetic energy of the bar, let's for just a time being talk about these three blocks first. Because I think after we talk about these three blocks, we could expand it to include the entire bar. Is that okay? So the kinetic energy of the three blocks together would be the kinetic energy of block 1 plus the kinetic energy of block 2 plus the kinetic energy of block 3. This would be the kinetic energy of the three block system. Eventually we'll expand it to be the whole bar, but right now we're just talking about these three blocks. Now, each one of these blocks has a different amount of kinetic energy. Even if we assume all the blocks are the same and have the same mass, they're all moving at different linear velocities. It might be better for us in the long run to try and find some common variables, if there are any, to describe the rotation and kinetic energy of the block. I note that all three of these blocks are part of the same bar and therefore have the same rotational speed. Right? They're all part of the same bar, so they're all spinning at omega. It seems not unreasonable for me to perhaps do some substitution. I think I could describe where each block is by saying that block 1 is distance r1 away from the axis of rotation. Block 2 distance r2 away. And although block 3 is on the other side, that would technically make its displacement negative. It's on the other side. I want to hold that idea in my mind for just a minute, that if these two are considered positive distance away from the axis, the other one being on the other side is a negative distance away. A whole number line thing. Either way, I could still write this out. So subbing in for V2 and subbing in for V3. Okay, so far? Now you realize omega is the same for all of them. And the 1/2 is there for all of them. So I'm going to do what I think is obvious, but maybe not obvious for you guys. I want to factor out the things that are true about my system, that are the same about my system. For example, they all have a 1/2 in them. They also all have an omega squared in them. Now, I'm not doing this for like just to be mysterious. I think you guys know why I'm doing this. And if you don't know, kinetic energy equals 1/2 inertia times velocity squared. For something that rotates, I'm trying to put this in terms of rotational velocity. I want to see if there's something I could put in the middle here that would represent the inertia. That's what this whole conversation is about. What is this rotational inertia component? What's left in the middle here would be m1 r1 squared plus m2 r2 squared plus m3 r3 squared. The first thing I want to throw at you is that notice all the values for r are squared here, which means it doesn't matter whether you're on one side of the bar or the other. Because I square it, the fact that it's on one side or the other doesn't matter. That inertia isn't about what side I happen to be on, just how far away I am from the axis of rotation. That's incredibly important, and I would really like you to kind of drill that into your notes, that it looks like the inertia of our system is more about how far away from the axis I am than anything else. That value is squared, which takes away anything about direction, also making it more important than the mass itself. Next, and I hope you see this, I left room in here. You realize that if I wanted to do this for the whole bar, I would merely need to add this up for every block that makes up the whole bar. And I see a clear pattern here. Do you see the pattern? That it's each individual mass times the distance away from the axis squared. So I do it for all the pieces that make up the whole bar. This is what's known as the moment of inertia. It's sometimes referred to as the rotational inertia. I've never heard it called the angular inertia, but I have heard it called the rotational inertia before. And they've used rotational inertia on exams before. But the technical name is moment of inertia, and there's a good reason why it's called the moment of inertia, so I'll be coming to that in a minute. But I want to explain a little bit of this. But did everybody see that derivation okay? So let's define a few things. I'm going to move that to here. Moment of inertia is often represented by an uppercase I. That's the first thing I want to say. This particular arrangement of the moment of inertia can be expressed as a summation. And for those of you who maybe not be as familiar with summation as others, you'll notice that everything appears to be the same, meaning it's always a mass times a distance squared. So if I can take an object and break it up into pieces, the moment of inertia will be the sum of each individual piece, starting with piece number 1 and going all the way to the last piece, piece number n. So if you're unfamiliar with the way a summation works, I is a placeholder. It tells me that for each mass and each distance, I need to find each mass and distance, multiply it together in this way, and do that from the first piece of mass to the last piece of mass. Sound familiar? Summations are not things you may have used very often before. And if you haven't, I don't care. This is what's known as the point mass representation of moment of inertia. It only works if you have something that can be broken up into pieces. I've given you this for homework. In your homework assignment, there's like a couple of examples of like a couple of pieces of objects, or an object that's made up of little points of mass. It's relatively straightforward, but I want to point out this is one way of calculating the moment of inertia. In order to use this calculation, your object needs to be something that can easily be divided into pieces. Not everything can. So most things can't. Most things will require an alternative to this. But there are examples where this works. So in your notes, a couple of things to put in. This is just a summation. That part I'm not worried about. So if you had 5 objects, you would do mr squared for each object and then add them all up. It could be something simple as I have something here, something here, something here, and something here. Right, just four balls. And maybe my axis of rotation is the middle, and they're going to spin like this. Well, this would be really easy to do. I would find out how far away this first one is. I would do mr squared for that one. And then I'd find out how far away this one is and do mr squared for that one. Not hard. On the other hand, it's called the moment of inertia on purpose. If my point of rotation was here, then suddenly the same 4 objects would have a different moment of inertia because now their distances are different because the axis of rotation has changed. So I would need this distance and this distance and this distance. And you'll notice one of the points doesn't contribute at all because it's on the axis of rotation. Good so far? All right. Now, if you haven't already put this together, that also suggests that we can write rotational kinetic energy as 1/2 I omega squared. I is all of this, but we can write rotational kinetic energy as 1/2 I omega squared. Now, because I want to be thorough, I gave you a one-dimensional example. But just I want to be clear. Imagine I have I don't know, potato. Imagine I have a spinning potato that has a axis of rotation here and is spinning like this. If I was successfully able to break the potato up into a bunch of little pieces of potato, I could have a piece here, perhaps, bless you, a piece here, maybe a piece here. And we could recognize that in my potato diagram, there's R1 to this piece, which has a velocity of V1. And then there's R2 to this piece, which has velocity V2. And of course, R3 to this piece with velocity V3. Does it really matter that it's not one-dimensional? It's about how far away each piece of mass is from the axis of rotation, regardless of whether it's one-dimensional, two-dimensional, or three-dimensional. the way I would describe the mass would still be the same. So this definition of moment of inertia doesn't matter whether your object is shaped like a bar or a potato. It's all about the distance of each mass to the axis of rotation. That is the most important part or quality of moment of inertia. From you. You see, right now, we've been playing with the kid gloves. And I don't mean like today, I mean this whole semester. We've been playing with the kid gloves. Because we've really arguably done our best to stay away from some hard math. The second semester, though, the kid gloves have to come off. We have to do the real thing. You see, the meter stick can't be broken up into little pieces. It's a continuous object. So the meter stick truly can't be treated as a point mass. In fact, the situation in which you can treat something as a point mass is actually pretty limited. You can only use the point mass formula for objects where the axis of rotation is outside of the object. I'll say that again. The only time you can really use the point mass formula for a moment of inertia is when the axis of rotation is outside the object. So like if I have a ball on a string and I swing that around my head, well, I could use the point mass formula. The axis of rotation is the end of the string. The ball's at the other end of the string. That's a point mass. The Earth and Moon, I could probably treat that as a point mass system. The axis of rotation is outside of the Moon for sure, and almost outside the Earth. I could probably treat that as a point mass system. The meter stick, well, unless I'm spinning it on a string far away, I'm likely going to be unable to use the point mass system. So we need to find a way to move from the point mass system to a type of mathematics that can describe a continuously massed system. That's going to be harder. That means finding a different way to break it up. And even if you've had calculus, you probably have not been trained on how to do this. Because my understanding is that you're probably just getting into basic integrals in calculus if you're in AB. Although BC has been doing integrals in calculus, the thing that everybody should be a little bit wary of is that they give you the integral, you execute the integral. That's like telling you to multiply 6 times 3 and you knowing that it's 18. The integral part is just knowing the product. Us, the hard part is why did you choose 6 and 3? We have to build the integral, and building the integral is the hard part. That's the part that is not taught in calculus. That has to be taught here. So we'll learn how to build the integral that can then be used to determine a moment of inertia. It is the most challenging thing we do in here. I don't want to make any small part about it. It's challenging. However, it's on the exam. You have a 1 in 5 shot of having to do it on the exam. Generally, you can lose those points and still get a 4 or 5 on the exam. But they can only give us 3 different shapes. I think we can learn those 3 shapes. Now, that being said, what I would like you to do is a little bit simpler. We're going to do one of these right now. There's a way to estimate it. This is what you suckers have been doing in calculus, where you take that curve and break it up into lots of little rectangles. Here's the version of physics for that. I'm going to take a meter stick, and I'm going to break it into 10 point masses. Meaning I'm going to take and divide it up into 10 centimeter segments. There. 10 centimeter segments. Make sense so far? And I'm going to assume that the center of mass of each segment is at the middle of that 10 centimeters. I want to compute the moment of inertia about the end of the meter stick by using the point mass formula. Remember, the point mass formula is mr squared, and I'm going to sum for every piece of mass. I'm breaking a meter stick up into 10 pieces of mass, so I is going to go from 1 to 10. Let's consider point mass 1. I don't know the mass of the meter stick. I'm going to assume my meter stick is of uniform density, so the first piece has mass m over 10. Does that make sense? All right. You might not be this quick, but the value for R, 5 centimeters, right? The middle of a 10 centimeter piece is 5 centimeters, and that must mean that this is 5 centimeters from the end to the first center of mass. So my first piece will be m times 5 squared. Are we good so far? I've got 10 of these to do. This is piece number 1. So piece number 2, I'm sorry, it's m over 10. M over 10. Sorry, m over 10. Piece number 2 has mass m over 10. It also has its center at the 5 centimeter mark, but it starts 10 centimeters away. So how far away is its center from the axis of rotation? 15. So plus m over 10 times 15 squared. You see where this is going? You got 8 more of those put together. When you're done, you will have the moment of inertia of the meter stick in terms of its mass. Not particularly hard to do, I hope. And we are not going to finish this, although we have 2 minutes left. I think you could finish this if you wanted. And you probably should if you're confused. If you're not confused, then I want you to be better and recognize that I chose a meter stick because it's 100 centimeters long, which means this could be a bar of length L, and the first center of mass is 5% of L. So you smarties could put this in terms of L if you want. That would be better for you if you could do that. But even if you can't do that, if you can do this part all the way to the end, then you can do my assignment this evening, tonight, and tonight only. It's due tomorrow when you come into class. I want you to do this exact thing again, but for breaking the same meter stick up into 20 pieces, not 10. This one you should finish. I've already set it up for you. You should finish it. But you should do it again for 20 pieces. I have a reason for doing this. It doesn't seem clear now, but everybody who's in Calculus AB knows why I'm doing this. I'm making the interval size smaller to show that it is a better and better approximation. So you guys in Calculus already are doing this. You guys not in Calculus, you need to see it. And this is how I've chosen to show you. But you have to do the legwork tonight. So tomorrow you should come in with some number times m for a 10 piece, and then some number times m for 20 pieces. And I'll be here in the morning if you need help. All right.